In this situation, we have an object, a point P, in water and the observer outside the water in air where the eye has been drawn. Now, there is a difference when we have the object and the observer in the same location. For example, if they were both in the water, both in air, because the ray would go straight into the person's eye. But in this case, the ray does not go straight in the person's eye. Um, we can see this effect when, for example, we immerse something in a glass of water. We don't see exactly where the object is, we see like it's closer to us. For example, when we have a ray that goes out like this here, then we have a normal, and then we have a normal that um, we can draw on, that is basically along this point, that is on this point, sorry, not like this or like this, and on the other side as well. We find that the angle between this ray here and the normal is that water would not be the same ray that is in between the ray in air and the normal. For example, it's gonna be like this. As you can see, the angle is very different. The angle is very different right here. Um, this is because the index of refraction of the two object of the two compound. For example, we know that the n of water is equal to about 1.33, so 4/3, while n of air is instead, well, to put it easy, is equal to 1. So the two angle would not be the same because the two index of refractions are not the same. Now, how do we relate these two angles? Well, there is a simple law called Snell's law that relates these two. And for example, it relates it like this: n of the first one times sine of the first angle, and we'll call angle 1, equals to n2 times sine of the angle 2. Angle 2. Oops. Now this is fairly easy and doesn't take much to realize that the bigger the n, the smaller the angle. For example, n of water is bigger than the n of air. N of water is 1.33, while n of air is 1. So the angle 1, in this case, n1 is n of water, and n2 is n of air. Angle 1 will be, of course, smaller than the angle 2 because the n is bigger. Now, let's make an example. Let's say the angle 1 was equal to, let's say 30 degrees. Then, through Snell's law, we can find that angle 2 equals to the sine of power minus 1 of n1 times sine of angle 1 divided by n2. So now, if we put it in calculator, we'll find that the angle 2 is equal to, well, sine of minus 1 of 1.33 33 times sine of, we said 30 degrees, divided by n2, so 1, it equals to 41.80, 41.68, sorry, equals to 41.68 degrees. As we said, since n of air is smaller than n of water, the angle in air will be bigger than the angle of water because sine is bigger with a bigger angle. Now, there is a few exceptions to this, not exception, but there is a limit. For example, if we have an angle that is, let's say 89 degrees to make it as clear as possible. So let's draw something that is about 89 degrees. Not too easy, but okay, so we have this angle at 89 degrees right here. This angle is, sorry, uh, this angle is actually 1 degrees. I have, um, I made a mistake by saying it. Well, we need an angle that is, as I said, 89 degrees. So let's go back. So we have an angle, right, let's say right here, and let's imagine that this angle, that the ray like this forms, is 89 degrees. Let's say this angle was 89 degrees. So let's call it angle 1, I'd say. Let's not cancel this thing, so we don't need it. We're just gonna cancel this thing here because we don't need them anymore. And we're gonna cancel this one. Now the calculations have to be done again. But now, if we plug in the number and we say that angle 2 equals n1, sorry, sine of power minus 1 of n1 times sine of angle 1 all divided by n2, we get a weird thing with a angle 1 to be equal 89 degrees because we do not get an actual value. The problem is that we have a angle that is way too big. Indeed, if you put it in a calculator, you will get an error of domain because we will get an angle, we will get a sign in here, a value in here that is bigger than 1 to show. We have sine of power minus 1, so n1 times sine of n1, so we have 1.33 times sine of angle 1, so sine of 89, it's actually 0.9994847. These two multiplied and then divided by 1, so we can just avoid running it. So we get a value of 1.329797. And sine power minus 1 of this number is impossible because, of course, the biggest number the sine can be is 1. So sine of power minus 1 of this number doesn't exist. So we find a point where actually no ray is reflected on the other side. So for example, there's no ray coming out of the water here and going to the other side. This ray does not exist at all. So where is the limit between the two angles? What is the limit of the angle that P can have? Well, it's very easy to find. We know, of course, that the calculations are this, so we can say that the biggest number that um, sine the number inside this parenthesis can be is 0, because that angle would be 90, and even then we wouldn't have a uh, angle out, we wouldn't have a ray that we can actually see, but there'll still be a ray because it's 90 degrees. It would be just a ray along the surface. So we would need to be along the surface to see the ray. So the point is that in order to find that angle, in order to find the so-called crater angle, because it's called crater angle if you need to find what is the biggest angle that it can be, the calculations are not hard at all. Indeed, the only thing that you need to find is they need to do is actually just put in correlations the two um, index of refraction. In fact, the critical angle, so the biggest angle that you can have, or at least the sine of the biggest angle you can have, is simply so sine of critical angle equals n of the second material, so not where the object is but where the observer is, divided by the index of refraction of the material where the object is. And that's the critical angle. In this case, we can simply find that the critical angle for us is equal to sine at the power of -1 of 1.1 divided by 1.3333. So the calculations are very easy, and the answer is 48. Sorry, let me write that a bit better. Okay, so the critical angle is actually equal to 48.61 rounded. So that's the critical angle. That means that the angle, the biggest angle that there can be of angle 1 can be is 48.61. So if we have an angle that starts from uh, the object P and it goes to 48.61, so let's say like this, with the normal, we would have a critical, we will find the critical angle. So if say this angle right here was this angle right here was 48.61, we would have a ray on the other side that is equal to 90 degrees. So it would be perfectly along the surface. Now it's hard to see with the red. This one is the critical angle. Um, anything anything closer to the surface, anything smaller for angle 1, of course, will give us a ray that goes on the other side, more toward the right, closer to the normal, and an angle on the other side will not give us any ray coming out. So now the question is, where how does a ray reach the observer? Well, we said that the angle has to be smaller in the water and bigger in the air. So let's start drawing an angle, a line from point P. Let's say it goes here. Then we have a, let's find the angle with the normal, like this. This is the angle with the normal inside the water. And as we said, the angle with the normal outside the water in air will be bigger because the index of refraction is smaller. So for example, it will be bigger like this. So we can see that the angle right here in between the ray in air and the normal in air is bigger than the light ray in water and the normal in water. But where will observer see the object? Because in this case we have some problems, since the ray does not come out of the object, the rays come out of another place. Seems like the observer will not see the object where it is. That is obvious because, for example, when you put a object inside the water, inside a glass of water, you don't see the object where it actually is. You see it in a different location. that is actually closer, and we can find the location by doing this simple thing. We have to backtrace this light ray that comes out of the um, the air. So let's backtrace it like this. Let's say it goes down like this. As you see, it does not go and intersect the ray inside. It does not go in and touch the object inside the water. It would go away, and then we backtrace this as well, because this is another ray, and we find that the location of the object is the location that the object that we see is actually at this point right here. Let me make it a little clearer. It's at the intersection of these 2 points. So right here. Now we can make it. We can check it by doing another thing. For example, whoops, we know that there's a ray coming out straight out of the object and goes perpendicular to the um, surface of the water like this. And this line actually has an angle of 0 with the normal line. This ray has an angle of 0 with the normal line. That means that the angle on the other side, thanks to Snell's law, this one right here, Snell, oops, law, gives us a angle 2 that is the same, because 0 on one side will be 0 on the other side, so the angle would just keep going the same way on the other side as well. So just copy it straight like this. Now we can backtrace that angle as we saw, but backtracing would just bring us back to where we were a second ago. So we will go back here where we said the intersection of the two or other races. So the location of the image is at this point. Now the location of the image is usually called P with a little apostrophe. Okay, let's put it in red so we know that it's the image this time. So the object is actually farther or deeper in the water than the image location, but the observer sees the image location, not the object location.